There's a relationship between CAD and hand sketching, and there's a line you need to keep between the two, whereby the CAD could help you with your hand sketching. There's nothing wrong with getting the zones and the scale set out and start tracing over that, but there's a process where you're thinking in that tracing period, testing out ideas, moving around, and you can do that a lot quicker often than sitting behind a CAD. And also telling the final story by hand is quite an important part of that, because it also says that this isn't finished yet. You want to have that room for future maneuver at the early stage of the design. With the building facade, it's quite exciting because it's the nexus of many disciplines, and the starting point usually is the architectural intent. What does the architect actually want to see? And that brings you across a wide range of options, from glazed curtain walling to quite solid masonry facades with punched windows. But because it's the nexus of disciplines, it also has to perform from a structural perspective, from a thermal perspective, from an acoustics perspective, from a fire perspective, etc. First of all, we need to establish where in the world this building is. If it's near the equator, we'll be designing it differently than if it's, say, in Europe. This has to do with the thermal properties that we want to get out of the facade. This has to do with the angle of the sun hitting it and the temperatures that we'll be dealing with. So that will influence the G values we're choosing for the glass, for example, or if we're going to be having brise-soleil or lots of insulation to get the U value that we need. The G value is a ratio of the amount of sun energy hitting a building and the amount that actually gets into the building. U value is a measure of the energy itself, a measure of the rate of energy that leaves the building. If I'm working with a tall building, I'll almost certainly go for a unitized system. This is a section through a mullion, and the unitized system is very quick to build because each unit comes in and clips into place. It allows movement to be accommodated between the units. But on the flip side, it has typically a wider section than, say, a stick system. Stick systems, typically less expensive, typically more narrow sections, but they take longer to construct, and the accommodation of vertical movement is possible, but you usually would use them in a stack system, and if you are stacking them, you would do that over a shorter height to make sure that the sections don't get too bulky. Starting with the structure, what we can do is first look at the wind loads and what's acting on the glass. That will size our glass panel. Once we know the size of the glass panel, which will also be influenced by the thermal performance, because we'll need a cavity, we'll need to know if it's a double glazed or a triple glazed. The combination of those two pieces of information will then tell us how heavy the glass is. Those loads then get transferred back to the mullions and transoms. A mullion is just a horizontal structural member in a facade, and a transom is a vertical member. Once we get into the size of the loads that are actually going in, we start sizing those up. And depending on if we have a stick system or unitized system, that will influence the width of the joint, and therefore then the depth as well. On this example, we have a unit, so it's a unitized system with a few stick elements actually within the unit. And zooming in to a 1:5 scale, we can start to see what that unitized system looks like. We have those two pieces that interconnect, and when we start drawing this up, we'd start with blocks, and we'd start from the outside in. So we know that how much space we need for the structure to work, and we'd start by just getting a block in there. And then that block will be sculpted out as we start to look at how the joint, the silicon comes in, how the carrier frame interfaces with the mullion. The carrier frame is how we attach the glass to the mullion or transom. And then initially, you're all working with zoning. You have a zone for your glass, you have a zone for your mullion, so you know what the structure is. You're also going to allow a zone for your fireboarding and for your acoustic separation, your acoustic barrier. You'll allow some room for your connection back to the slab. You'll have a slab thickness. All these things together start to build up the outline blocks, which later on you sculpt into. And that's really good to start doing that with a pencil or a pen or whatever, to really start to dig in and carve out what the detail is from that block. When is it necessary to change scales? Well, we would start with a scale of 1 to 10 when we start looking at the more macro level of the loads coming onto the mullions. We would go into a smaller scale, 1 to 2, 1 to 1, when we start looking at the actual section extrusion itself and its interfaces with the glass and gaskets and joints and silicon. What we have here is a vertical section through the facade, and that lets us look at a slice through the slab edge and how it interfaces with the facade. Working on our way out, we can see what the buildup of the facade is. At the top we have number 5, which is a double glazed unit. Below that, we're interfacing with a panel that has number 6, GRC, glass reinforced concrete. Behind the glass reinforced concrete we have a cavity to ventilate it so that moisture doesn't build up. And then we have number 15, which is a water barrier. Then we have the insulation, which is number 7. And as we move in, we have other important components to divide the floors up from each other, acoustically and from a fire protection point of view. So what we have is number 11 is we have some intumescent paint, which is painted on to a bracket, number 10, which is fixed to the underside of the slab. And this is where it's important, even that level of detail, to get those small parts that all interface and are quite important to the integrity of the facade and the fire barrier. What we're trying to do here with the colors is give some contrast to actually bring out these elements. When they're black and white, they're also legible, but here it makes it very distinct where one material starts and one material ends.
So the first setting is the urban street setting. This allows the building to respond to the street and the ground level. It's usually within a more dense built-up area. It gives you the opportunity to respond to adjacent or neighbouring buildings. The second setting is the riverside setting. This allows for opportunity to respond to the river and to maximise views across to landmarks or buildings across the river. And the third setting is the office park setting. This is usually like a mini master plan, which is designed for the function of an office park or a business park. And it gives the building more room to provide opportunity to play with form and height. So this drawing is scale 1 to 100. It's a typical office floor plate, and the lines here denote the structural grid, which is set out to a multiple of 1.5 metres. 1.5 metres square is the UK design standard for a planning grid for office buildings, and it provides the optimal layout for an office building in terms of furniture and in terms of circulation. So this is a section through the building which is taken through the central core. Key aspect to office design is the core, and the accommodation in terms of toilets and vertical circulation is designed within this area. The section also shows in a little more detail the toilet and kitchen spaces. Zooming in on the accessible toilet within the core, we have a drawing here which is at scale 1 to 50. It lays out the sanitary ware within the toilet and shows elevations or sectional elevations which indicate the ceiling and the ceiling void, which can be used for services. We would send this drawing on to the engineers who would produce an overlay at a larger scale. This is zooming in at 1 to 20. This allows them to lay out the services within the room. This drawing shows diagrammatically the ventilation services and the pipework required for this area.
I'm Chris Wise. I'm an engineer and a design professor. I'm just going to talk about how to tackle the way you might put a relatively simple building in 3 different sorts of sites. And it's a 4-story building. It's got a little basement, and the 3 sites are firstly close by a river, and secondly in a big open office park setting where maybe it's a brownfield site or a greenfield site, and lastly tight on the corner of an urban street where you're close by roads and other buildings. First thing you do is you work out what it is you're trying to carry. So you work out the weight of the building, and for this one, rough rule of thumb is the building weighs 1 ton for every square metre of floor, so it's about 5 floors, 400 square metres of floor, that's 2,000 tons. So I know I've got to carry 2,000 tons. The second thing you have to worry about is what is the ground that the building is going to sit on. So, and if it's mud, then obviously it's not great. If it's rock, it's fantastic. If it's something in between, that's okay. And you're thinking about what's around the building as well. So other roads, other structures, other buildings, and that sort of thing. And the last thing you have to worry about is if there's any water in the ground, because that affects the way you might build something. We start with the relationship between carrying the weight of the building and what the ground is made of. The first thing you would do is literally draw the I'd finish the building and have all these loads coming down, and I would say, right, I now know from the site investigation that we've got, let's say there's some earth on the top, and then there might be sand and gravel down below. In London you have clay a bit further down, so let's say we've got clay down here. And if this is a relatively light building, so what choices have you got for foundations? Well, you say, well, I could just put some big pads sitting on the gravel, and that's probably enough in London to carry the load. So there are lots of buildings built with that sort of foundation solution, and that would be fairly simple. If the ground was really rubbish, so say it was silt or something like that, and then you have the building, you have the loads coming down, and let's say there's a lot of, this is all soft material up here, and there's something a bit firmer down below, so I'll put something firmer down below. Then normally what you do is put piles in, so you can go for a deeper sort of foundation which enables you to take the loads of the foundations and put them much further down into the ground onto something solid, and that's what you do. And so there's a physical relationship between the geometry of the ground and its arrangements and the weight of the building coming down. If you're working close to a river, what you need to worry about is water. Rivers are full of water, and so that probably means the ground close to the river is also likely to have water in it. So if you're putting a basement close to a river, the question is, how close to the river are you? The further away you get, the less water. The closer you get, the bigger the problem with the water. And so normally what happens is you end up having to put some sort of cut-off, which is a protection wall or some device which enables you to stop the water getting into your construction, which then means you can then build something in the dry. So it might be a sheet pile wall or a diaphragm wall or something. The other thing you need to worry about is usually, especially in cities, the rivers have already been confined by a river wall, and those walls can be very old. They're often listed, historic monuments. Quite often they have things tying them back to stop falling over. And if you go really close to your historic river wall, and of course people want to be close to the river, you may find yourself cutting away the very thing that's stopping that wall falling over. And so you have to think of a way of stabilizing that wall, sometimes by building something on the back of it, sometimes by tying it onto your building, all sorts of things. And so building close to rivers, you have to worry about water and protecting your basement from that, but also making sure that you don't destabilize the very thing that's stopping the river becoming a lake. So if I'm looking at an office park site, the first question I would ask myself is, what has been there on that site before? Have human beings been building stuff for the last 1,000 years? Are there old industrial works there, gas works? Is there something in the ground? And the reason that I'm interested in that is because, is there anything noxious, nasty down there which will actually either be unsafe when we're trying to dig it out, or maybe some sort of chemical which will affect the structure that we're going to put in there. So you need to investigate what's happening, and then let's say that it's a nasty site. The first thing you'd end up doing is saying, right, there's a big old industrial crane base or something sitting right where we're trying to put our building. So the first thing you've got to do is get rid of that. You've got to take it out. And so there would be a little exploratory thing to find out where they are, and then you would have to come up with a construction program to get rid of those safely before you build your new building, so sort of pre-construction. If it's nasty ground, what you might say is you actually have to either what's called remediate the ground, which make it safe, by mixing it with other materials, or actually take away the nasty soil and replace it with clean ground, and then you can build in there. So old quarries and things like that are typical of that sort of thing. Railway yards. So, but apart from that, an office park is relatively straightforward and easy because there's not much round about it, and if there is anything, it's new, so you can design it specifically. And so what you end up doing is just carrying the weight of the building, choosing pads or piles depending on whether it's soft ground or good ground further down, and think a little bit about the water in the ground, but it's a very simple operation once you've cleaned the site. So if you're trying to build in the middle of a city in an urban street, you have to think about a few different things, and it can be quite complicated because you have you want to build your new basement, but often people have built there before, so you usually find yourself grappling with existing foundations. So there may be, let's say, Victorian brick foundations or something like that. Or if it's a new building, you may have piles which you've got to get rid of. So you need to take those away safely. You probably, for most urban projects, there would have been a basement on the site already, or for many of them, at which point you've got to worry about the existing basement wall, which may not be very important for you, but it's really important for the street next to you, because if you don't have a wall, the street will fall into your site. And usually in the street in a city, you've got sewers and you've got power lines and you've got fiber optic and all sorts of things, which people take a really dim view if those start moving around. And also what you have to think about is, well, I'm going to be taking hundreds of tons of material out of this site, thousands of tons in some cases, and if I take that off, probably what will happen is the ground will go up as it's unloaded. It'll go back down again once I put the new building in, but in the meantime it goes up, and you don't want the street to go up because the sewer might not work anymore. And so often you end up thinking about, well, what can I do to control those movements? And so building in cities is all about controlling movements, and so people end up designing things which might be actually deeper foundations which go down to take the loads further down so the movements are smaller, or deeper walls around the edge and that sort of thing, maybe more props internally and all that sort of stuff. And the reason they do that is because they're not so much worried about carrying the weight of a building. It's not that heavy really, but what they're really worried about is destroying the ground that is supporting somebody else's building or the city's streets or infrastructure, and people don't like that if you ruin their stuff.